All right, now we're going to talk about multiple regression, where instead of just having one independent variable, we have multiple independent variables. Should be noted that there's only one dependent variable that we can have, only one outcome that we're interested in. There are some statistical techniques where we could use multiple dependent variables, but that's a little more, well, actually a lot more sophisticated than just regression. So we can only have one dependent variable, and it has to be quantitative. But our independent variables, we can have innumerable ones, and they can be quantitative or categorical. We'll take a look at that here with this data. Let me tell you a little bit about what we're looking at here. We have data from a company that manufactures boiler units for big industrial companies. And when they get a job, they have to come up with a price. How much are they going to charge for this custom-built boiler unit? So it's important that they be able to predict how long it's going to take them to build it, therefore they can figure out how much cost is going to go into it. So we're going to try to come up with a formula that can predict the number of man-hours, our dependent variable here, based on 4 different potential independent variables or factors that we think might influence that number of man-hours. The first one we see is the capacity. How large, in terms of gallons, is this boiler drum? Second one is the pressure. How many pounds per square inch will it have to hold up to? Our third and fourth independent variables here, you can see, are categorical variables. They're noted as 1s and 0s, and that's what we have to do to get them to come out in a regression equation, is to take our different categories, assign 1 to one category and 0 to the other category. And that's what's been done here. For the boiler unit, I don't know what these terms mean, but if it's an industry field boiler, then it's noted as a 1. If it's a utility field boiler, then it's noted as a 0. We don't really have to know what those are. It would be important to that particular company. The drum itself, if it's a steam drum, it's a 1. If it's a mud drum, it's a 0. Again, I don't know what those two differences are, but it would be important to that company, and they feel like it's important to determining how many man-hours go into the project. Let's take a look at how we would do this in StatCrunch. We'll go to Stat and Regression, and now it's going to be a multiple linear regression because we have more than one independent variable. Our Y, or dependent variable, is going to be the man-hours that it takes. And our other 4 variables, capacity, pressure, boiler, and drum, let's hold Control down and select all of them, those are our X variables. There's also an option to use interaction effects, but we're not going to be dealing with that. All we have to do is choose the columns that we're interested in as independent variables. And then there's one more little thing that we need to do. We'll scroll down here, and when it comes down to variable selection, we want to choose the stepwise method, and we want to set our p-value to enter to be 0.05, our normal p-value that we've been working with for months and months and months. What the stepwise method does, instead of just throwing all of those independent variables in at once, it looks at the most significant variable first, puts that in, and then rechecks the other variables to see if any of the others are still significant. And it just goes through them step by step, so you don't end up with any variables in your model that don't have a significant predictive effect on that dependent variable. I'm going to click Compute. And we get our results here. The first thing that we have to do is look down here to our overall p-value, less than 0.05, so we're good. We do have a significant predictive equation. And we can see up at the top table under our steps, we did end up with 4 steps. we ended up with all 4 of those variables entering into the equation as a significant predictor of our man hours. The first variable, the most significant predictor, was the capacity. And in fact, if you look at the R² value there, you can see that capacity alone accounted for almost 70% of the variability in the man hours. Next, we had the drum, whether or not it was a steam drum or a mud drum. That was the next most significant predictor, and that put us up to almost 86%. The boiler, and then the pressure, and finally we end up at an R² value, or predictive value, of almost, just slightly over 90%. Our equation, we could again look here in our parameter estimates and generate our equation. We'll take those here and write them out. Our equation would be that our man hours, or our dependent variable, is equal to negative 3,783 plus 0.0087 times the capacity. So with every gallon of capacity that we add into the boiler, it adds a little bit less than 1/10 of a man hour to the job, plus 2,093 times drum. Now you may remember, I'm going to switch markers here because that one's not working very well. You may remember that for the drum variable, we coded it with a 1 if it was a steam drum, and a 0 if it was a mud drum. Well, if the drum variable comes in with a 0 as a mud drum, 0 times anything is 0. So that item just falls out of the equation. It's only if it's a steam drum that we multiply 2,093 times 1, then it's going to add 2,093, a little over 2,000 hours to the job. Similarly with our boiler, we have an estimate of 3,444 times boiler. So if the boiler comes in as a 1 type, it adds 3,000 plus hours to the job, plus 1.93 hours times the pressure. So as the PSI that it has to withstand goes up by 1 unit, it adds 1.93, or almost 2 hours to our total job. And we could then take this equation and put in whatever values we have for our proposal for the client, put in what that's going to be, and come out with an estimate of the man hours that it would take to do the job. And with our R² value, we could see that that's explaining 90% of the variability of man hours. One other point that I want to make right now, and then we'll look at one more example, is beta 0, our intercept value, by itself typically is worthless. It doesn't really mean anything. If all of these other things were zeros, then where this equation would intersect the y-axis would be at negative 3,783. Well, can we possibly have negative 3,783 man hours in a job? No. But can we possibly do a job where we have no capacity, no drum, no boiler, no pressure? No. It's not going to hold up. The intercept by itself really doesn't give us any meaningful information. But it's needed in the equation to combine with everything else to make that predictive equation work out. I want to take a look at one more, and that is going to involve the data file called APTS, which stands for apartments. And this is data taken from Minnesota. We have a code here that's just like an ID number. We have the selling price of various apartment buildings. We have the number of apartments that were included in that apartment building, the age, how many years ago it was built, the lot size, how big the land that goes along with that apartment building was, the number of parking spaces that go with it, and the building area, how many square feet are in the building itself. They also have a condition, fair, excellent, good, or poor. That, because there are multiple options there, that would involve a technique called dummy coding if we wanted to include that, and we're not actually getting into that. So we're just going to ignore the condition variable for now. And we're going to try to predict the selling price of an apartment building based on these other quantitative variables. We'll do that by going to our stat button, regression, and multiple linear regression. Our y variable is the selling price, and then we have the number of apartments, the age, the lot size, the number of parking spaces, and the building area, all as x variables. Whenever we're doing a multiple regression, we want to scroll down and choose the stepwise method with a p-value to enter of 0.05, and we click compute. And now let's see what we got. Overall, our predictive model is significant. P-value overall is less than 0.05, so that's good. The variables that entered into the equation are significant predictors of the selling price. But notice we had 5 different independent variables here, and only 3 of them actually made it into our equation. The building area, the number of apartments, and the age of the building. The lot size and the number of parking spaces weren't important in generating that selling price. One other thing to notice here, our R-squared value for the third model that includes the building area, the apartments, and the age of the building is almost 98% in explanatory power. So those 3 items alone are explaining almost all of the variability in those selling prices. If we were to create our equation here, we would have the intercept as 114,368. Building area is $14.96, or in other words, for every square foot of size of the building itself, it's adding about $15 to the selling price, over and above that base value. For every additional apartment in the building, it's adding just over $5,000 on average to the selling price. And for every year old that building gets, it takes away just over $1,000 from that selling price. So again, if we had an apartment building we were looking to try to sell, we could plug those values for building area, number of apartments, and age into that equation and come up with a pretty good prediction of what we might be able to sell that for. Another thing, remember the intercept, that $114,368 by itself really doesn't tell us anything, because that would only be valid for an apartment building with no square footage, no apartments, and no years old, so it wasn't even built yet. So just the beta 0 or the y-intercept alone doesn't really tell us anything. Thank you.